The grandfather paradox. Imagine stepping into a machine that hums like a caged storm, your creation, your doorway into yesterday. You travel back in time with a purpose, or maybe just curiosity. The world smells different. The air feels untouched. And somewhere in this unfamiliar past, you meet a young man, your grandfather, long before he became anyone's grandfather. And then something goes wrong. Maybe it's an accident. Maybe it's fate. Maybe it's your own clumsiness or an ill-timed moment of chaos. But in this fragile slice of history, your grandfather dies before he ever meets your grandmother. And that's where the universe starts to fold in on itself. If he never meets her, your parent is never born. And if your parent never exists, you don't either. Which means you could never have built a time machine, never traveled back, never caused his death. So he survives, which means you are born, which means you do go back, which means he dies again. You can almost hear reality glitching like a broken record. A cause erasing its own effect, an effect erasing its own cause. A loop with no beginning and no end. So the question becomes, does the universe even allow this kind of paradox? Or does something deeper, something unseen, protect the timeline from collapsing? One idea says yes, reality fights back. It's called the Novikov self-consistency principle, and it claims the past is completely locked. You can visit it, walk through it, breathe its ancient air, but you can't change the events that led to your existence. Not even slightly. Aim a weapon at your grandfather? It misfires. Try to interfere? Circumstances twist themselves to stop you. Even your own emotions might betray you at the last second. It's as if the universe itself refuses to let contradictions happen. But there's another possibility, more dramatic, more unsettling. Hugh Everett's many worlds interpretation suggests that every choice, every action, every tiny vibration in the quantum world creates a new branch of reality. So if you go back and end your grandfather's life, you don't erase your own timeline. You simply jump onto a new branch, a universe where you will never be born. You're still alive, but you no longer belong anywhere. A temporal exile, a traveler from a history that no longer touches the one beneath your feet. No paradox, no contradiction, just an endless forest of parallel worlds, and you standing in one you were never meant to see. So the real question becomes, if time travel is possible, which universe would greet you on the other side? The Fermi paradox. Look up at the night sky for a moment. Really look. Every point of light you see, every flicker, every shimmer, is a star burning unfathomably far away. And our galaxy, the Milky Way, holds somewhere between 100 and 400 billion of them. Now zoom out even further. The observable universe contains roughly 2 trillion galaxies. Trillions of cosmic islands, each bursting with stars, each with planets, and many of those planets sitting in the so-called Goldilocks zone, where liquid water could pool, oceans could form, and life, at least life as we understand it, could take root. And the universe has had 13.8 billion years to make it happen. With numbers this enormous, with so much time and so many chances, intelligent civilizations shouldn't just be possible. They should be everywhere. But when we listen, when we point our instruments into the abyss, we hear nothing. No signals, no probes, no alien ruins drifting between the stars. Just silence. A silence so complete it becomes unsettling. This is the Fermi paradox, named after physicist Enrico Fermi, who famously blurted out a deceptively simple question during lunch in 1950. Where is everybody? Statistically, the galaxy should have been explored long before humans ever lit their first campfire. A civilization even slightly more advanced than ours could unleash self-replicating probes, machines capable of hopping from star to star, until the entire Milky Way was mapped within a few million years. A mere cosmic heartbeat. If they existed, we should see something. Beacons, megastructures, alien scrap metal, anything. Instead, nothing. So what's going on? Why does the math say the universe should be overflowing with intelligence, while the evidence suggests we're sitting here in an empty theater? This brings us to one of the most unsettling ideas in all of science, the great filters. A great filter is some enormous barrier that prevents life, from simple microbes all the way to star-faring societies, from advancing to the next stage. And the terrifying twist is that we don't know whether this filter is behind us or waiting ahead. Possibility 1. The great filter is behind us. Maybe the hardest step wasn't building rockets or inventing quantum mechanics. It was life itself. The leap from lifeless molecules to the first self-replicating organism might be so ridiculously improbable that it happened only once in the entire universe. In that scenario, we're the lucky ones. The only spark in a cosmic ocean of darkness. Incredibly special and profoundly alone. But then comes possibility 2, the one that keeps astrophysicists awake at night. The great filter is still ahead. Maybe life is common. Maybe intelligence is common. But some catastrophic threshold, destroys every civilization before it can spread to the stars. What could it be? Maybe societies always invent technologies faster than they develop wisdom, leading to nuclear wars, ecological collapse, rogue nanotechnology, or a runaway super AI that wipes out its creators in minutes. If that's true, the silence of the universe isn't comforting. It's a warning. But there are other possibilities too, less apocalyptic, but just as eerie. The zoo hypothesis suggests that alien civilizations are out there, but they're deliberately avoiding us, watching from a distance, following a strict policy of non-interference. Earth, in this view, is a protected exhibit, and we are the unaware animals inside it. Then there's the dark forest hypothesis, perhaps the most chilling of all. In a dark forest, every creature hides. Every whisper is dangerous, because anything you reveal can get you killed. Maybe the universe works the same way. Maybe intelligent civilizations stay silent, because broadcasting your location is like lighting a flare in the middle of a cosmic wilderness. And something stronger, something older, might be listening. So the question becomes, is the universe empty? Or is it full? So full that everyone is hiding? Olber's paradox. Here's a question so simple it feels almost childish, yet its answer reshapes everything we know about the universe. If space is full of stars, then why is the night sky dark? This is Olber's paradox, named after the 19th century astronomer Heinrich Olbers, though thinkers had wrestled with it long before him. Imagine the universe is infinite. Imagine it has always existed. Imagine stars are scattered everywhere in every direction. If that were true, then no matter where you look, left, right, straight ahead, your line of sight should eventually hit a star. Not empty space, not darkness, a star. Picture standing in an endless forest. No matter where you look, you see a tree. In an infinite universe, every direction should reveal the luminous surface of a star. If that's the case, the entire night sky should blaze like the surface of our own sun. No darkness, no night. Just a sky filled edge to edge with starlight. But that's not what we see. Instead, the night is filled with vast oceans of blackness between the stars. So something in our assumptions must be wrong. And the solution to this paradox uncovers one of the most powerful arguments for the Big Bang. First, the universe is not infinitely old. It had a beginning, about 13.8 billion years ago. That means we can only see light that has had enough time to travel across space and reach us. If a star sits 20 billion light years away, its light hasn't arrived yet. Its part of the sky remains dark simply because its photons are still en route. The observable universe is a bubble defined by the speed of light, and we're at the center only because we are the observers. Beyond that bubble lie countless stars, but their light has yet to touch us. Second, the universe is not static. It's expanding, rapidly. And the farther away a galaxy is, the faster it's racing away from us. As space stretches, it drags the light traveling through it. The wavelengths get pulled longer, shifted from visible light into infrared, into microwave, even into wavelengths our eyes could never detect. This cosmological redshift means that much of the light from distant galaxies arrives drained of energy, or doesn't arrive at all. Some regions of the universe are receding so fast that their light will never reach us. Not in a trillion years. Not ever. So the night sky is dark for two profound reasons. Because the universe has a beginning, and because the space between galaxies is expanding, stretching ancient starlight into invisibility. The darkness above us isn't empty. It's the echo of the Big Bang, and the long shadow of an expanding universe still racing away into the unknown. Now the question becomes, if darkness tells us so much about our past, what else might it be hiding? Schrödinger's cat. Few thought experiments are as famous or as wildly misunderstood as this one. A cat, a sealed box, a bit of radioactive material, and a challenge to everything we think we know about reality. This is Schrödinger's cat, a puzzle designed not to confuse you, but to expose just how strange the quantum world truly is. The idea came from physicist Erwin Schrödinger in 1935. Picture a bizarre chain reaction device worthy of a dark cartoon. A closed box, a living cat inside, a tiny sample of radioactive material, unstable and unpredictable. This radioactive atom has a 50% chance of decaying within an hour and a 50% chance of doing nothing at all. Completely random, completely quantum. Beside it sits a Geiger counter. If the atom decays, the counter detects it. That detection triggers a tiny hammer. The hammer breaks open a vial of deadly hydrogen cyanide. The gas spreads. The cat dies. If the atom doesn't decay, nothing happens. The vial stays whole. The cat lives. You close the lid. And now the experiment begins. In ordinary life, common sense tells us something obvious. The cat is either alive or dead. We just don't know which yet. But quantum mechanics doesn't care about common sense. According to the Copenhagen interpretation, dominant at the time, the atom exists in a strange limbo called superposition. Until it's observed, it is both decayed and not decayed at the same time. Not metaphorically, literally. And because the cat's life depends on that atom, the cat becomes part of the superposition. Inside that box, in the eerie quiet of the sealed chamber, the cat exists in two states at once, fully alive and fully dead. A quantum ghost of possibility. Schrödinger hated this idea. He didn't propose it because he disliked cats. He proposed it to show how absurd it was to apply quantum rules to everyday objects. A superposition might make sense for a single atom, but a living creature? How could reality hold both outcomes at once? According to this interpretation, everything hinges on observation. The moment you lift the lid, the wave function collapses. Reality makes its choice. The cat snaps into a single definite state, one you finally get to witness. But that raises a disturbing question. What counts as an observation? Does it have to be a human? What if a mouse wandered inside the box? Would the universe collapse then? This is the measurement problem, one of the deepest riddles in physics. But there's another interpretation, one that escapes the paradox entirely at a cost. The many worlds interpretation says the wave function never collapses at all. Instead, when the atom enters its superposition, the universe branches. One universe where the atom decays, the poison releases, and the cat dies. Another universe where nothing happens and the cat lives. Both outcomes are real. Both unfold. Opening the box doesn't force reality to decide. It just shows you which version of the universe you ended up in. In this view, the cat is never both alive and dead simultaneously. The paradox disappears. But in its place, a multiverse blooms, splitting, branching, multiplying endlessly. And if that's true, then every choice, every possibility, every quantum flicker might be creating new worlds in the shadows of our own. Now, if a cat can break the rules of reality, what happens when we do it? The twin paradox. Time feels universal, unchanging. A minute should be a minute for everyone, no matter who you are, where you stand, or how fast you're moving. But then Einstein arrived and shattered that intuition completely. His theory of special relativity showed something radical. Time is not absolute. It bends. It stretches. It marches at different speeds depending on how fast you travel. And that revelation leads directly to one of the strangest and experimentally verified paradoxes in all of physics, the twin paradox. Imagine two identical twins. Let's call them Alice and Bob. Alice stays on Earth, living her life at normal human speed. Bob, the thrill-seeker, climbs into a futuristic spacecraft and blasts off toward a distant star, accelerating until he's traveling at 99% the speed of light. He races through deep space for several years, then flips his ship around, turns back, and returns home at the same blistering velocity. Now here's where reality bends. According to special relativity, the faster you move, the slower time flows for you. Your heartbeat slows. Your aging slows. Your entire experience of time stretches out. So when Bob steps out of his spaceship, he may have aged only a handful of years. But Alice? She may have lived through decades. Bob has effectively leapt into the future without ever leaving the present. And this isn't theory. It's been confirmed using ultra-precise atomic clocks flown on jets and satellites. Moving clocks really do tick more slowly. But here comes the paradox. From Bob's point of view, he was the one at rest inside his ship. From his perspective, it was Earth and Alice that sped away from him at 99% the speed of light and later rushed back. So shouldn't Alice be the one who aged more slowly? Both twins see the other as the one in motion. Both expect the other to be younger. Who's right? The key is hidden in a single word: acceleration. Special relativity treats all motion as relative, but only for frames moving at constant speed. In reality, Alice remains in one calm, nearly inertial frame the entire time. She never rockets away. She never brakes. She never turns around. Bob does all of those things. He accelerates to near light speed. He decelerates at the far end. He reverses direction. He accelerates again. He finally slows to a stop when he reaches Earth. Each acceleration is a jolt, a shift from one frame of reference to another. That break in symmetry is the entire solution. Bob's journey wasn't smooth. It wasn't inertial. It involved violent changes in velocity that Alice never experienced. And those shifts carve a real, measurable difference in aging. The traveling twin, the one who accelerates, always ends up younger. The paradox isn't a contradiction at all. It's what physicists call a veridical paradox, a result that feels absurd, yet is undeniably true. So if you ever hope to stay young, the secret isn't a better moisturizer. It's a spaceship capable of outrunning light itself. Zeno's paradoxes. Imagine taking a simple step forward and discovering that, according to one of history's sharpest minds, that step is logically impossible. Nearly 2,500 years ago, the ancient Greek philosopher Zeno of Elea created a set of arguments that attacked the very idea of motion, space, and time, and he did it so elegantly that his paradoxes puzzled humanity for 2 millennia. Start with his most famous one, the dichotomy paradox. You decide to walk from one side of a room to the other. Easy. But before you can cross the whole distance, Zeno argues you must first cross half. And before you can cross that half, you must cross half of that. A quarter, then an eighth, then a 16th. The distance keeps splitting forever. Every step requires completing an infinite sequence of smaller steps. But how can you finish an infinite number of tasks in a finite amount of time? According to Zeno's logic, you can't. Motion, he said, is an illusion. Then comes his most iconic thought experiment, Achilles and the tortoise. The legendary Greek hero races against a turtle, but gives the slow creature a head start. By the time Achilles reaches the point where the tortoise began, the tortoise has moved ahead a little. Achilles sprints to that new point, and once again, the tortoise has crawled a tiny bit farther. This repeats infinitely. Achilles always gets closer, but never quite catches up. A swift warrior defeated by pure logic. For centuries, these paradoxes weren't just clever riddles. They pointed to a deep flaw in human intuition. Our minds struggle to imagine infinity. The idea that dividing a distance forever could somehow prevent motion felt disturbingly airtight. And for more than 2,000 years, nobody had a mathematical framework to break Zeno's spell. That changed with the birth of calculus. Mathematicians finally discovered that an infinite series doesn't always stretch toward infinity. Sometimes, it converges to a very real, very finite value. Take the sequence Zeno uses. 1/2 plus 1/4 plus 1/8 plus 1/16. Add it forever, and it doesn't explode into infinity. It lands exactly at 1. The distances get smaller so quickly that their infinite total becomes perfectly finite. The same is true for the time it takes to travel them. Infinite slices, finite sum. Zeno wasn't wrong. He was pointing to the limits of human intuition long before mathematics could explain them. His paradoxes don't prove that motion is impossible. They prove that reality follows the rules of calculus, even thousands of years before we invented the language to understand it. The bootstrap paradox. This is one of the strangest ideas in all of science and science fiction, a paradox that attacks the very concept of creation itself. It's called the bootstrap paradox, also known as a causal loop or ontological paradox, and it describes something deeply unsettling, an object, a piece of information, even a person, that has no true origin. It exists because it causes itself to exist. Here's the classic example. A devoted Beethoven fan travels back to the 18th century, eager to meet the legendary composer. He brings along Beethoven's complete sheet music, every symphony, every masterpiece. But when he arrives, he discovers something horrifying. There is no Beethoven. The man never lived. None of the music exists. In a panic, the traveler decides the world must not lose these masterpieces. So he publishes the sheet music himself under the name Ludwig van Beethoven. The compositions become famous, shaping centuries of music, and eventually inspiring the very time traveler who brings them into the past. So who wrote the symphonies? Not Beethoven. He never existed. Not the traveler. He merely copied what he already had. The music has no origin. It simply loops through time, self-created, self-sustained. That's the bootstrap paradox. Information pulled out of the void, like lifting yourself by your own bootstraps. A logical impossibility made real. Now imagine this paradox applied to a physical object. An inventor creates a one-of-a-kind pocket watch. Through time travel, he hands it to his younger self. That younger self grows old, then gives the same watch to his even younger self, and the loop continues forever. At no point is the watch ever manufactured. It just exists, eternally handed down through the timeline. But here physics pushes back. The second law of thermodynamics states that entropy, disorder, always increases in a closed system. A real watch would scratch, rust, and wear out over time. An object trapped in an endless loop should eventually become nothing but dust. Yet in the paradox, the watch stays pristine. That shouldn't be possible. So what does this mean? Either causal loops like these cannot exist in our universe, or our understanding of causality, entropy, and information is missing something profound. In the strange logic of time travel, maybe not everything needs an author. Maybe some things simply drift through time in perfect, originless loops, stories with no beginning, because the beginning was never written. The black hole information paradox. For more than 50 years, physics has been ruled by two towering giants, two theories so successful, yet so completely incompatible, that they seem to be daring us to reconcile them. General relativity, Einstein's masterpiece, rules the cosmic stage. Planets, stars, galaxies, and the monstrous gravity wells known as black holes. Quantum mechanics, on the other hand, governs the tiny, chaotic, probabilistic world of atoms and subatomic particles. Each theory works flawlessly in its own realm, but the moment you force them together, reality starts to crack. And nowhere is that crack more violent than in the black hole information paradox. The setup. According to general relativity, a black hole is gravity turned up to infinity. Cross the event horizon, the point of no return, and nothing, not even light, can escape. Whatever falls in is gone forever. Quantum mechanics says absolutely not. A foundational rule of quantum theory is that information can never be destroyed. Burn a book and you turn pages into ash, smoke, and heat. But the information about its atomic structure still exists, just scrambled. The universe never loses track of the details. So what happens when you throw that book into a black hole? Relativity says the information is lost forever. Quantum mechanics says information cannot be lost. Ever. These two perfectly proven theories cannot both be right. Hawking's bombshell. In the 1970s, Stephen Hawking unleashed the grenade that made this paradox unavoidable. By merging relativity with quantum field theory, he found that black holes aren't perfectly black. They emit a faint glow, Hawking radiation. This radiation slowly drains their mass until, after unimaginable spans of time, the black hole evaporates completely. And that's when the paradox becomes a crisis. When the black hole disappears, where did the information go? If it vanished, quantum mechanics is wrong. If it escaped, general relativity's description of black holes is wrong. One of these foundational theories must give way. There is no middle ground. The battle for reality. Physicists have proposed all kinds of reality-bending solutions, hidden in the Hawking radiation. Maybe the information does leak out, not in the energy of the radiation, but in subtle, tangled quantum correlations inside what looks like random static. The universe whispers secrets in the noise. The holographic principle. A far more radical idea. The information never enters the black hole at all. Instead, it gets stored on the event horizon, on the 2D surface, like a cosmic hard drive. In this view, the interior of the black hole is an illusion. Even more shocking, many physicists now think our entire 3D universe may work the same way. A holographic projection of information encoded on a distant 2D boundary of spacetime. The black hole information paradox isn't just about black holes. It's about the nature of space, time, reality, and whether the universe you think you're living in is even real in the way you imagine. The observer's paradox. Here's a simple, frustrating truth. You can't observe something without changing it. In the social sciences, this is familiar territory. Watch someone carefully, and they behave differently. People become self-conscious. They act how they think you expect. Observation contaminates reality. You can never see the pure version. But in the quantum world, this paradox goes far deeper. It's not psychology, it's baked into the universe itself. At the subatomic level, particles like electrons aren't tiny solid points. They exist as a wave function, a fuzzy cloud of probability representing all their possible positions, speeds, and properties at once. An electron isn't somewhere. It's everywhere it could be, all at the same time. The moment you try to measure it, the universe draws a line. You interact with the particle, maybe by bouncing a photon off it, and suddenly, the wave of possibilities collapses. The electron picks a single location. Your act of observation has changed reality. What was a cloud of potential becomes a definite particle. This is the root of Heisenberg's uncertainty principle. There's a fundamental limit to how precisely certain properties can be known at once. Measure an electron's position exactly, and its momentum becomes fuzzy. Measure its speed exactly, and its location blurs. This isn't about imperfect instruments. It's a property of reality itself. The universe, at its core, is fuzzy. It's not a fixed stage waiting to be discovered. It's a participatory process. The properties of the world aren't defined until they are measured, and that raises the same puzzling questions as Schrödinger's cat. What counts as a measurement? Does a conscious observer matter? Or is any interaction enough? The observer paradox in quantum physics tells us something profound. We are not passive spectators of reality. We are active participants, shaping the universe simply by trying to understand it. The simulation argument. This may be the most unsettling paradox of them all, one that doesn't just question physics or time, but reality itself. The simulation argument, most famously presented by philosopher Nick Bostrom, doesn't insist we are living in a simulation. Instead, it argues that one of three possibilities must be true, and two of them are incredibly bleak. Here is Bostrom's trilemma. At least one of the following must be true. Proposition 1, the doomsday scenario. Civilizations like ours almost always go extinct before they reach the technological level needed to create ultra-realistic simulations of their ancestors, simulations filled with conscious, thinking beings. In this view, humanity doesn't survive long enough to play God. Something wipes us out first: war, plague, AI, or an unknown catastrophe lurking ahead. Proposition 2. The apathy scenario. Advanced civilizations do survive and do develop the capability to run simulations, but choose not to. Maybe they find it immoral to create conscious beings who can suffer. Maybe they've evolved past the point of caring about their primitive history. For whatever reason, they have the power to simulate universes, but they universally refuse to. Proposition 3. The simulation scenario. We are almost certainly living inside a simulation. This is where the logic becomes brutally statistical. Assume the first two propositions are false. That means advanced civilizations survive, thrive, and run countless ancestor simulations. A single post-human civilization could create billions, even trillions, of simulated universes, each containing billions of simulated minds like ours. If that's true, then simulated realities would outnumber base reality by a staggering margin. Simulated minds would vastly outnumber biological ones. So if you randomly find yourself as a conscious being somewhere in the multiverse, which population are you more likely to belong to? The tiny handful of real beings, or the overwhelmingly huge ocean of simulated ones? Statistically, the odds aren't just high, they're almost certain that you're in a simulation. And here's the ultimate twist. If humanity ever creates its own ancestor simulations, it would strongly confirm that we ourselves are simulated. A simulated world creating its own simulations. A recursive chain with no clear starting point. Are there glitches in the matrix we can detect? Déjà vu? Strange quantum randomness? Physics constants that seem too perfectly tuned? Or is a perfect simulation indistinguishable from reality, making the question unanswerable by design? Even if we are simulated, does it matter? Your food still nourishes you. Your love still feels real. Your pain still hurts. But the thought lingers, like a background process running quietly in your mind. Everything you know, your life, your memories, the universe itself, may be nothing more than a line of code running on someone else's machine. If you love diving into mind-bending ideas like this, make sure to subscribe to Strange Wise for more mysteries that challenge reality itself.